just wanted to add a word, like, what I meant was describe how the majority of the oxygen and the majority of carbon dioxide. It doesn't compare with the other 2%. Does it?
Well, they, yeah, it's kind of through the majority for the 70% for the
70% is what?
It's transported by
Biocarbonate.
yeah,
By bicarbonate ions?
Okay. So don't worry about the other 30%.
Yeah, we'll just do those. So I think one of the problems with these is if you look on the top of the book or other places, I think they usually just say it's this volume plus this volume minus this volume. Is that kind of what y'all were finding? I think it's a lot easier to think about them as what it actually is. So like, what's the tidal volume?
The volume of the breath.
The volume of a normal breath. Then I guess we can go in order. So inspiratory reserve volume.
The forced air after the tidal volume.
So it's the additional air you take in with the forcible breath. Expiratory. What's the extra air you blow out? The forcible exhalation. So for both of those, like breathe out normally, that's the tidal volume, and then you breathe out more. Whatever else you breathe out is the expiratory reserve volume. So I think I'd rather you know that it's whatever formula they put in there. Like, no. We'll practice with the actual numbers in lab. I guess this week probably we'll find them. And then the residual volume. So that's like even after forceful exhalation, that's the amount of air left in your lungs. Did you know that you couldn't get all the air out of your lungs? I think I kind of just always assumed that you breathe all your air out. It's kind of a lot, right? I mean, 2 times as much as a normal breath just sits in there. Interesting, I think. Alright, now we went through all of them. So the amount of air remaining in the lungs after a forceful exhalation, residual volume, the amount of air left in there, the amount of air in a normal breath. Volume, most of the blood's oxygen is transported, hemoglobin, and most of the blood's carbon dioxide is transported. That's bicarbonate, and what is compliance? The effort required to expand the lungs. Most of the time people change their answers to the wrong thing. Alright, so if I find like a good movie that goes over something, so this is like a 4-minute lecture about this lung volume. Just want another review on it. Alright. So if you remember last time we talked about internal and external respiration. Part we didn't really talk about was ventilation, which really kind of comes first. So ventilation, of course, is the air going in and out of the lungs. Outside the lungs. That's ventilation. all controlled by muscles. Just a moment. So remember we talked about the pressure changes. So in order to change the pressure inside the lungs, or in the alveoli, exact, you contract and relax muscles. You can imagine, do you think you contract more muscles for forceful breathing? Yeah. We'll see how that works a little bit. So for normal breathing, it's mostly just two main muscles. The one you probably thought of already is the diaphragm. I'll do that. So when you're inhaling, the diaphragm pulls down, or contracts. It is external intercostals pull up, contract. And those external intercostals, they go from one rib to the next. So when they contract, they pull it up. So if you feel your chest, you're breathing, is your ribcage moving up a tiny bit? You're going to feel that. That's from those intercostals. So a combination of that one and the diaphragm makes the actual lung volume larger. Think of like inflating a balloon, like the balloon on it. And then for breathing out, well, you just relax. And then there's some of these other muscles for exhalation. Well, for the most part, normal breathing, we just have those two. And that. Alright, see that picture how you pull the diaphragm down, get a greater space. So, how do you, or why does contracting the diaphragm cause here? Yeah. All right. So the correct answer is actually E.
Well, he's considering all the right ones.
So diaphragm pulls down. Let's say you've got 50 gas molecules in there. Well, now you've got them full of balloon. Are they taking up more space or less space? More space, right? And at least right when that happens, that's actually the definition of lower pressure. So it would be to say lower pressure. That same amount of molecules in a greater space. Right? So inner molecules taking up more space. That's basically the definition of pressure. So decrease pressure, this one, and then as the molecules come in from outside, what happens to the pressure? It's going to increase to match whatever the outside pressure is. So there, and then of course when you exhale, wait, this is the question. Hold on, I can't remember if I have that. Very good. So when you exhale then, what happens? Which will be the answer for exhaling? Yeah, great. Great, all right. Well, definitely increases pressure. So it would just be A. Because then increase the pressure, and then you'd have to say the same number of molecules taking up less space. Which is not much of something. Because you're squeezing those. Increase greater pressure, and then they leave until they match the outside pressure. So it's not quite like, well, that sort of makes sense. So the pressure is why the air is going in and out. It's not like you're quite squeezing the air out. It's changing the pressure of it. Right, so let's get a few videos here.
During breathing, the intercostal muscles contract, pulling the rib cage upward while the diaphragm moves.
Videos, so I couldn't find one that shows both things. I like this one because it shows you how those external intercostal muscles work.
In cases of severe respiratory distress, the sternum will visibly retract as well.
Very beginning part. You can imagine each of these muscles pulling on the rib below it. You can see how it's kind of the chest is rising and the diaphragm is pulling down. So the internal volume is getting larger.
The origins of the external intercostals are from the inferior borders of the ribs above. The fibers pass obliquely and inferiorly to insert onto the superior borders of the ribs below. The external intercostals elevate the rib cage during inspiration. They are innervated by the intercostal nerves.
Forceful inhale. You can see all these different muscles are involved. So you've got some muscles pulling up from sternocleidomastoid, which comes up to the jaw almost, the neck pulling on the rib cage, pectoralis major, your pecs in the front here, contracting. Internal intercostal as well. The diaphragm's obviously all its own, right? You can almost think like nearly all of these upper body muscles are involved in forceful inhale. In your back, right? Your lat is back there. How much more air did you bring in? According to this single graph. Why don't you talk to group, see if you can tell me how many times more air do you bring in with a forceful inhale compared to a regular inhale based on that graph. Alright, the big stream. The big stream out. How many times more? It is 6 times. Right? About 3,100. A tidal volume is the normal gap. So that means with normal inhale, you bring in 500. Forceful inhale, you bring in 3,000. Just left like 6 times more.
Okay.
Was it the math stopping you or the graph?
The graph.
The graph, really?
Yeah. I don't really.
So it's kind of good because, you know, exercising or anything like that, you need a lot more oxygen, a lot more quickly. So you've got basically this reserve where your lungs can bring in so much more air. But you don't need all that air, you can just not waste energy. Like a nice slow roll breathing, not contract all the muscles. Which is good because if you couldn't do this forceful inhalation, you'd go walk real fast for 10 steps and then you have to stop and be like, sit there, catch your breath. You know, there wouldn't even be any deep breaths to catch your breath. It'd be like, you know, us normal people that can do that. You're hiking up like 15,000 feet uphill, you take like 5 steps, and you're like, or if you're like me and you're trying to show off for a girl, you're I'm just gonna run up this last part of the mountain. And if you don't, you ever try this, like while you're doing it, you feel kind of okay, and then you stop and you realize you can't breathe, and it's like laying on the ground and running. Yeah, exactly. Just like laying there. Can't breathe. It's not working. Alright, so this is a nice little diagram. Look like I've compared the quiet breathing. We've got those ones we talked about, the diaphragm next to the intercostal. We've got a whole list of forceful inhalation muscles. So go on to all those. And then forceful exhalation has chin bar muscles involved. You forcefully exhale, squeeze all that extra air out. And in lab, we've got these little machines where we can measure how much air you're breathing in and out. So for each person in here, we'll find out what your tidal volume is, what your inspiratory reserve volume is, expiratory. The only thing we can't measure, what can we not measure? Yeah, there's no easy way to measure them. Which makes you kind of wonder how they know what that number is, but how do they know? Yeah, but a lot of them are probably like, no, I don't know the answer. Oh, maybe it could be some kind of like enclosed chamber somehow. Maybe that's how they did it.
For us, I don't
That with the blood though. So tell us how it works.
Well, like when you bag somebody out, there's a chromatography that you can hook onto it, and then when you ventilate, and then it shows.
Besides the oxygen too. So you can see how much, like what CO2 percentage is coming out of their body.
Yeah.
What does that tell you?
It tells you if you need to ventilate more, or if you can get oxygen on that.
Okay.
And then they use it like when you're
What's the, what are the numbers, or what do you look for this per page? CO2 level.
it just depends. We use some type of, I mean, I only have this, I don't have any expiration, but they have some type of formula. So I know like if it's at a 7, it's pretty close to being gone, but.
Yeah, I would think, so that would be affected by like, how well the heart's pumping probably. If there's no blood getting through the lungs, then you're not gonna get a higher level of CO2. Right? So then if your heart's working well, you get higher CO2. Right? Well, I wonder if they have one of those tomorrow to measure people's CO2 levels in here. Interesting. To ask ENT people. Alright, which of these contract during quiet or, what I should say, a lot of times they use like quiet and normal interchangeably. Alright, so we got. So I can talk to your neighbor, talk about it. And I would suggest to read the question again too, make sure you're not answering something I think it says.
Yeah, I'm gonna wait to put it on. Yeah.
Final vote. Alright, so I'd probably shift to E, and I would agree with you. Because what happens to the diaphragm during exhalation? Is it contracting? It's relaxing, right? Internal intercostal is not really involved. So exhalation is mostly just relaxing. And there is like depends on the connective tissue in the lungs. They are elastic. So when you just relax these muscles, they're not being pulled on. So it's just like a rubber band goes back to its normal state. Right? It's uninflated state. Sort of is automatic. Just like when you blow up a balloon, if you let the air out, are you having to push on to let the air out, or it's just go back? There's no air in it, right? It does fly out of the air. Just like when you exhale, you want to fly across the
I was reading insulation.
So there. You know, I wonder, so if you're like in space, is that enough pressure to move you a little bit? There's zero gravity, breathe out. Yeah, but when you're in the spaceship, you're on the suit, and you're pressurized. So you just like, go like.
That's why I'm thinking
Yeah.
because the air.
Yeah, that's true. Yeah. So if they were outside, they couldn't swim, right? Get it back and put it inside. Getting off top of here. If you like sci-fi and safe. Alright, so I'm going to do another Venn diagram on your table. Your normal breathing, just quiet breathing. See any similarities with the kids that are on I think we got most of the markers right. If you happen to find any that aren't working well,
Venn diagram. Do you want more colors?
I'm sure they have at least 4 differences and I don't know, 3 similarities maybe. Let's do this. So if you are putting muscles down, make sure you say if they're contracting or relaxing during inhalation, exhalation, and show like what you actually.
But it's different from contraction.
Alright, so fun thing that group number 4 brought up is where does that extra air go in the forceful breath? You're bringing it up to the butt. Well, I'm sorry, I did a lot. So you're saying bring 500 mils in normal breath, and bring 3,600 in a forceful breath. Where's the extra air going? Think about it. Think about what you learned about lung structure last time. Is it all in the bronchus? Is it alveoli? Yeah, so in a normal breath, all your alveoli aren't getting filled up with air. Some of them are still kind of closed. In fact, probably most of them. So in a forceful breath, the deepest breath you could take, you're filling up all the alveoli. They're kind of closed, and they fill up. It's like the percentage of the air.
That way, like, when we have surgery.
They do what? Like during surgery or?
Like when you're, you know, pregnant. That way.
I still know that work with like the breathing tube? Yeah. Oh, I think so. Yeah. Yep. Oh, you're talking about the training thing?
Yeah.
Yeah. It's just, yeah, like you're breathing and that. And also train them.
So during the course of breathing, you're filling up all the alveoli. So what do you do during normal breathing?
So let's say you've got 100 alveoli.
Yeah.
In normal breathing, you're only filling up 20 of them.
Oh.
And the other 80 are mostly closed. Forceful breathing. Then forceful breathing, you're going to fill up all of them. And actually there's a mechanism for the blood to only go to the filled up ones. Because you wouldn't want to send your blood to the closed alveoli. That's called ventilation perfusion coupling. Very local. I mean, that makes sense. All right, so let's talk about how you control respiration. First up, can you hold your breath till you pass out and die? Anybody? Don't try it. Which means, would you say control of breathing is voluntary, involuntary, or both? It's both, right? It's kind of interesting. Which one wins, though? Eventually. So the two main important parts then are the cerebral cortex, which is the voluntary portion. Make yourself breathe deeply, hold your breath, whichever. And then there's also the involuntary portion, which is regulated by chemoreceptors. And you'll see lots of stuff with chemoreceptors throughout Bio202. And that's basically a neuron that has a receptor that can sense how much of something's in the blood. And for this one, it monitors how much of oxygen and CO2 are circulating in the blood. I don't know how it does that exactly. You see the bit. I mean, how would a receptor tell that? I'm not sure. It works, but it does work. It sends input to the medulla, which is where your basically the respiratory center is. It decides how fast you're breathing, how forceful, which is of course the brain stuff. Take a look at a few of these right now. First, you could go back through all of these if you wanted to.
Ventilation is rhythmic and involves continuous cycles of inspiration and expiration. Various regions of the brain closely regulate this rhythmic pattern of ventilation. The rhythmicity area in the medulla regulates the basic rhythm of ventilation. The medullary rhythmicity area contains two smaller regions, the inspiratory area and the expiratory area. During normal, quiet ventilation, only the inspiratory area is active, but during forced ventilation, both areas are active.
Why do you think that is? What last statement said? Only the inspiratory area is active. Normal breathing.
Normal breathing, you're not using any muscles to inspire.
Exactly. So you don't have to send the signal to the diaphragm to relax. This is automatically relaxing.
In forced breathing, the inspiratory area sends impulses to accessory inspiratory muscles, resulting in a more forceful inspiration. The inspiration area also activates the expiratory area during the expiration portion of the cycle. The expiratory area then sends impulses to expiration muscles, which consist of internal intercostals and abdominal muscles. These impulses cause the expiration muscles to contract, and this results in a forceful expiration. The rate of the ventilation can also be modified by input from other areas of the brain. Impulses from higher cortical brain centers can bypass the respiratory centers in the pons and medulla and provide us with some limited voluntary control over the muscles of ventilation. This pathway allows us to consciously alter our breathing patterns, which is necessary for speech or holding our breath. Changes in blood pH, partial pressure of carbon dioxide, and partial pressure of oxygen have profound effects on respiratory rate. Chemoreceptors in the central and peripheral nervous systems closely monitor the hydrogen ion, carbon dioxide, and oxygen levels in blood. Changes in the frequency of impulses from the chemoreceptors affects respiratory rate.
So don't worry about the pH levels for now. We'll do that. We'll get to that. Acid and bases chapter. So if you have high CO2 in the blood, what do you think is going to happen to your respiration rate? Okay, then you can walk to. Do you think it's possible for, or do you think those always happen together? Low oxygen, high CO2? You would think so. But as it's in later chapters, you have certain disorders where you can build up CO2 in the blood but have enough oxygen, or vice versa. We'll talk about how that works. But, so that's why you need both. So you just measure both. Because both things would be a problem, right? High CO2 or low oxygen. So if any of those things happen, you better change, right? Right, I just had an idea for one. Alright, so which is for the regulation of things. Okay, so if you chose active, right? There's all of those things. Voluntary is involuntary, which we would consider low oxygen levels with increased rate works. Right. So basically in every chapter you'll probably see a few of these. This is the diagrams the book uses to show the feedback loops for controlling something. In this case, this is for controlling your breathing rate, of course. And they'll always be the same. So there'll be some stimulus. In this case, it's either high CO2 in the blood or low oxygen. Then that stimulus activates receptors. You have receptors in two places, actually in the medulla, and then also in arteries like the aorta and carotid artery. Do you know where the carotid artery is? For the brain, right? So it's a pretty important place to have good oxygen flow. That's why the body has receptors there. And of course the aorta, that's where all the blood goes. It's a good place to measure it as well. Sends input back to the control center, the medulla, and whenever that stimulus is present, sends signals to the effectors, which are those muscles that cause forceful ventilation and exhalation. And if you're breathing harder or faster, what happens to CO2 and oxygen? CO2 would go down and oxygen would go up. And would that take away the stimulus? It would, right? So just a normal negative feedback there. Right. So we're gonna practice that a little bit. Let's talk about how exercise would affect everything based on that diagram. So if you're exercising, what happens to CO2 and oxygen in your blood? Okay, and why? Why does your CO2? What are you breaking down with CO2 again? You're not breaking down ATP. Where do you get energy from? From molecule. Glycogen, which turns into glucose. So if you're breaking down glucose, you're breaking CO2, and you're breaking down faster. You need more ATP. And why does your oxygen levels drop when exercising? What's that being used for? Muscles. Yeah, but inside a muscle, like a muscle cell is using oxygen for it. Yeah. So it's aerobic respiration to make ATP. So if you're exercising, your muscles are working harder, need more energy, so they break down glucose, make CO2, it needs oxygen to break it down. So that's why these changes happen right at birth. So how does the body respond? Well, forceful breathing, more rapid breathing, and also it's going to send more blood to the lungs, to the alveoli. So the blood changes the CO2 and oxygen better. And the bronchioles will dilate. So you can get more air into the alveoli. That mechanism as well. Does anyone have exercise-induced asthma? Heard of it maybe? Yeah. So if you do have it, exercise-induced asthma, you start exercising, and for whatever reason, your bronchioles will contract when you're afraid to exercise, or nothing, and it's not. It's a true condition. It doesn't just mean you're out of shape or something. You know, I used to tell my sister that. And one thing that can happen if you ever tried to exercise and it's really cold out. Yeah, and your bronchioles will constrict because there's a mechanism for not bringing too cold of air deep into your lungs to damage them. So that's why it's harder to exercise when it's really cold out. You're not able to breathe enough oxygen in. Especially here if you're out, trying to go snowshoeing and it's like 5 degrees or something. Probably not going to be able to bring in as much air as you need for that reason. Alright. So the other thing to look at is this crazy graph called the hemoglobin dissociation curve, which all it's showing you is down here at the bottom is how much oxygen is in the air versus what percent of hemoglobin has oxygen attached to it. So for example, if you have oxygen at 100 milliliters of mercury, which is just an amount of pressure, well, that's 100% saturated. So roughly, so with blood is when it goes back to the lungs, so, when it's going back to the lungs, it's down here to only 30% saturated. Because the partial pressure of oxygen in your muscles are contracting is much lower. So they've used it up. And then if you're not exercising as much, it's way up there at 70%. Which provides you another extra oxygen. Because even before you're breathing harder, your blood already has extra oxygen in, like at 70%. So you can exercise those muscles down to 30 before you actually have to breathe harder. Oh, one thing, or oh wait, yeah, I don't want to tell you that. So do that. Alright, so it's actually not 3, let's do 2 first. Which is the hemoglobin curve. That curve, A through E. Alright, so definitely bring this with you to lab tomorrow. We'll finish up this chapter before we do the lab. The lab's not super large.
There isn't
Too much talking about
this
space.
second, the third one, that's from the guide. And that one, kind of hard for me. The high altitude one. Where'd you find that one?
That's
I
right.
got the
That's
third
right.
one, I didn't get the high altitude.
But 2015.
Because in the book, it's like right
Figure
here,
out
you
what
have
you're
the
doing.
chart. Sorry, I have that on.
The third one, it's mainly because
Oh, yeah.
March is the air is still filling.
Yeah, that's, yeah. Yes,
So there's less surface area for gas exchange.
because they're, the alveoli. Yeah.
So they have 20
But I don't get,
millimeters.
I don't get the